This presentation is delivered by the Stanford Center for Professional Development.
So what I want to do today in this lecture is talk a little bit more about learning theory, and in particular I'll talk about VC dimension, and building on the issues of bias variance trade-offs, of underfitting, overfitting that we've been seeing in the previous lecture and that we'll see in this one. I then want to talk about model selection algorithms for automatically making decisions for this bias variance trade-off that we started to talk about in the previous lecture. And depending on how much time, I actually may not get to Bayesian statistics and regularization, but if I don't get to this today, I'll get to this in next week's lecture. All right. To recap, the result we proved at the previous lecture was that if you have a finite hypothesis class, if H is a set of K hypotheses, and suppose you have some fixed parameters gamma and delta, right, then in order to guarantee that this holds, with probability at least 1 minus delta, it suffices that m is greater than or equal to that. Okay. And using big O notation, so then drop constants, I can also write this as that. Okay. So just to quickly remind you of what all the notation means, we talked about empirical risk minimization, which was our simplified model of machine learning that has a hypothesis class of script H. And what the empirical risk minimization learning algorithm does is it just chooses the hypothesis that attains the smallest error on the training set. And so this symbol epsilon, this denotes generalization error, right? This is the probability of a hypothesis H hat misclassifying a new example drawn from the same distribution as a training set. And so this says that in order to guarantee that, oh, excuse me, makes no sense at all. Okay. In order to guarantee that the generalization error of the hypothesis H hat output by empirical risk minimization, that this is less than or equal to the best possible generalization error using in your hypothesis class plus 2 times gamma times 2 times this error threshold. If you want to guarantee that this holds with probability at least 1 minus delta, we showed that it suffices for your training set size m to be greater than or equal to this. Okay, 1 over 2 gamma squared log 2k over delta, where again k is the size of your hypothesis class. And so this is a sample complexity result because it gives us a bound on the number of training examples we need in order to give a guarantee on on something, on the error. Okay, so this is a sample complexity result. So what I want to do now is take this result and try to generalize it to the case of infinite hypothesis classes. So here we said that the set script H is sort of just K specific functions. What do you want to use a model like logistic regression, which is actually parameterized by real numbers? So I'm actually first going to give an argument that's sort of formally broken. It's sort of technically somewhat broken, but conveys useful intuition. And then I'll give the more correct argument, but without proving it, since the full proof is somewhat involved. So here's a somewhat broken argument. Let's say I want to apply this result analyzing logistic regression. So let's say your hypothesis class is the class of all linear decision boundaries, right? So say script H is parameterized by D real numbers. Okay, so for example, If you're applying logistic regression with over n features, then D would be n plus 1, because logistic regression defines a linear decision boundary parameterized by n plus 1 real numbers. If you think about how your hypothesis class is really represented in a computer, right? Computers use 0, 1 bits to represent real numbers. And so if you use like a normal standard computer, normally we represent real numbers via what's called double precision floating point numbers. And what that means is that each real number is represented via a 64-bit representation, right? So really, you know what floating point is in a computer. So a 64-bit floating point is what almost all of us use routinely. And so if it's parameterized by D real numbers, that's really, as if it's parameterized by 64 times D bits. Right? Computers can't represent real numbers. They represent these discrete things. And so the size of your hypothesis class in your computer representation, you have 64 times D bits that you can flip. And so the number of possible values for your 2 to the 64 D bits is really just 2 to the power of 64D, okay? Right, because that's the number of ways you can flip 64 D bits. And so this is why it's important that we had log K there, right? So K is therefore 2 to the 64D. And if I plug it into this equation over here, what you find is that in order to give this sort of guarantee, it suffices that m is greater than or equal to on the order of, I guess, 1 over gamma squared log 2 to the 64D over delta, which is that, okay? So just be clear, in order to guarantee that, so we're interested in the same sample complexity result as we had before. So the question is, suppose you want to guarantee that the hypothesis returned by empirical risk minimization will have a generalization error that's within 2 gamma of the best hypothesis in your hypothesis class, right? Then what this result suggests is that, in order to give that sort of error-bound guarantee, it suffices that m is greater than or equal to this. In other words, that your number of training examples has to be on the order of D over gamma squared times log 1 over delta. Right? And the intuition that this conveys is actually roughly right. This says that the number of training examples you need is roughly linear in the number of parameters of your hypothesis class. That m has to be at least on the order of something linear in D. And that intuition is actually roughly right. I'll say more about this later. But, so let's see. What was I saying? But, this result is clearly slightly broken in the sense that it relies on a 64-bit representation of floating point numbers. So let me actually go ahead and outline, the quote right way to show this more formally, right? And it turns out the quote right way to show this more formally involves a much longer, it requires a proof that is extremely involved. So I'm just actually going to state the result but not prove it, for how to prove these sorts of learning theory bounds with infinite hypothesis classes. So this definition, given a set of points, let's see. So given a set of D points, we say a hypothesis class H shatters the set S if H can realize any labeling on it. Okay, and what I mean by realize any labeling on it, the informal way of thinking about this is if a hypothesis class can shatter the set S, what that means is that I can take these D points And I can associate these D points with any set of labels Y. Right? So choose any set of labeling Y for each of these D points. And if your hypothesis class shatters S, then that means that there will be a hypothesis that labels those D examples perfectly. Okay, that's what shattering means. So let me just illustrate that with an example, I guess. So let's say H is the class of all linear classifiers in 2D. Right? And let's say that S is this data set comprising 2 points. Okay? So there are 4 possible labelings I can choose for these 2 points. I can choose to label both positive, one negative, one positive. I can label both of them negative. And if the hypothesis class H is class of all linear classifiers in 2D, then for each of these training sets, right, I can sort of find a linear classifier that attains 0 training error on each of these, on all possible labelings of this set of 2 points. And so I'll say that the hypothesis class script H shatters the set S of 2 points. Okay. It's one more example. So, slightly larger example. Suppose my set S is now this set of 3 points, right? Then I now have 8 possible labelings for these 3 points. Let's see. Okay, and so for these 3 points, I now have 8 possible labelings. And once again, I can, for each of these labelings, I can find a hypothesis in my hypothesis class that labels these examples correctly. And so once again, I see that, by own definition, I'm going to say that my hypothesis class also shatters this set S. Right? And then the terminology, H can realize any labeling on S. That's all this means. It means you can give it any set of labels, and you can find a hypothesis that perfectly separates the positive and the negative examples. Okay. So how about this set? Oops. Suppose S is now this set of 4 points. Then there are lots of labels. There are now 16 labelings I can choose on this, right? That's one, for instance, and this is another one. Right, and so I can realize some labelings, but there's no linear decision boundary that can realize this labeling, and so H does not shatter this set of 4 points. Okay, and I'm not really going to prove it here, but it turns out that you can show that in 2 dimensions there is no set of 4 points that the class of all linear classifiers can shatter. Okay, now. So here's another definition. I'm going to say that it's called the VC dimensions due to 2 people, Vafnik and Shervoninkis. So given the hypothesis class, the Vafnik-Shervoninkis dimension of H, which we usually write as VC of script H, is the size of the largest set that is shattered by the set by H. And if your hypothesis class can shatter arbitrarily large sets, then the VC dimension is infinite. So just as a concrete example, if H is the class of all linear classifiers in 2D, then the VC dimension of the set is equal to 3, because we saw just now that there is a size of, there was a set S of size 3 that it could shatter, and I didn't really prove it, but it turns out there is no set of size 4 that it can shatter, and therefore the VC dimension of this is 3. Yeah.
But there are sets of size 3 that cannot shatter, right?
Yep,
Recalling your point.
Yep, absolutely. So it turns out that, you know, if I choose a set like this, if that's my set S, then there are labelings on this that cannot realize, and so H cannot shatter this set. But that's okay, because right, the def is there exists some other set of size 3 that can shatter, and so the VC dimension is 3. And it turns out, and there is no set of size 4 that can shatter. Yeah. Not according to this definition, no. Right. So again, let's see. I can choose my set S to be, you know, I can choose S to be sort of 3 points that are all overlapping, right? 3 points in exactly the same place. And clearly I can't shatter this set, but that's okay. And I can't shatter this set either. But that's okay, because there is some other set of size 3 that I can shatter. Okay. And it turns out this result holds true in 2D. More generally, you know, in n dimensions, the VC dimension of the class of linear classifiers in n dimensions is equal to n plus 1. Okay, so this is in 2D. If you had linear classifiers over an n-dimensional feature space, the VC dimension in n dimensions, right, is nd, is equal to n plus 1. So let me now write down what is, I don't know, what is arguably the best known result in all of learning theory, I guess. Which is that, let a hypothesis class be given. And let the VC dimension of H be equal to D. Then with probability 1 minus delta, we have that actually, let me write this. The formula on the right looks a bit complicated, but don't worry about it. I'll point out the essential aspects of it later. But the key to this result is that if you have a hypothesis clause with VC dimension D, and now this can be an infinite hypothesis clause, what Vafnik and Chovanenko showed is that with probability at least 1 minus delta, you enjoy this sort of uniform convergence result. Okay, excuse me. We have that for all hypotheses H. That for all your hypotheses for all the hypotheses in your hypothesis class, you have that the generalization error of H minus the training error of H. So the difference between these two things is bounded above by some complicated formula like this. Okay, and thus, with probably 1 minus delta, we also have that well, that same thing. Okay, And going from this step to this step, right? Going from this step to this step is actually something that you saw yourself, that we actually proved earlier. Because you remember, in the previous lecture, we proved that if you have uniform convergence, then that implies that, in the previous lecture, we showed that if generalization error and training error are close to each other, within gamma of each other, then the generalization error of the hypothesis you pick will be within, 2 gamma times the best generalization error, right? So this is really generalization error of h hat is less equal to best possible generalization error plus 2 times gamma. And there's a 2 constant in front here that I've absorbed into the big O notation. So that formula is slightly more complicated. Let me just rewrite this as a corollary, which is that, in order to guarantee that this holds with probability 1 minus delta, with probably at least 1 minus delta, I should say, it suffices that, I'm going to write this way. I'm going to write m equals big O of d, and I'm going to put gamma and delta as a subscript there to denote that, let's see, if we treat gamma and delta as constant, so if you allow me to absorb terms that depend on gamma and delta into the big O notation, then in order to guarantee this holds, it suffices that m is on the order of the VC dimension of the hypothesis class. Okay? So, let's see. So what we conclude from this is that if you have a learning algorithm that tries to, for empirical risk minimization algorithms, in other words, let's say, less formally, for learning algorithms that try to minimize training error, the intuition to take away from this is that the number of training examples you need is therefore roughly linear in the VC dimension of your hypothesis class. And more formally, this shows that sample complexity is upper bounded by the VC dimension. Okay? It turns out that for most reasonable hypothesis classes, it turns out that the VC dimension is sort of very similar, I guess, to the number of parameters in your model. So for example, you have a model like logistic regression, like linear classification. In n dimensions, right, logistic regression in n dimensions is n plus 1 parameters. And the VC dimension of logistic of the class of linear classifiers is also n plus 1. So it turns out that for most, sort of quote, most reasonable hypothesis classes, the VC dimension is usually, linear in the number of parameters of your model, or at most some sort of low-order polynomial in the number of parameters of your model. And so the takeaway intuition from this is that the number of training examples you need to fit most models is going to be, let's say, roughly linear in the number of parameters in your model. Okay? There are somewhat strange examples where what I just said is not true. There are some strange examples where you have very few parameters, but the VC dimension is enormous. But I actually know of all the examples I know of that fall into that regime are, somewhat strange and degenerate. So somewhat unusual, and not the sorts of learning algorithms you usually use. Let's see. Just other things. It turns out that, so this result shows that sample complexity is upper bounded by VC dimension. That if you have a number of training examples that's, on the order of the VC dimension, then you're fine. It turns out that in the worst case, and this caveat in the worst case is important, but it turns out that in the worst case, sample complexity is also lower bounded by VC dimension. And what that means is that if you have a particularly nasty learning problem, say, then if the number of training examples you have is less than on the order of the VC dimension, then it is not possible to prove this bound. So I guess in the worst case, sample complexity of the number of training examples you need is upper bounded and lower bounded by the VC dimension. Let's see. Questions about this? Yeah.
Does the proof for this assume any sort of finiteness, like you have to discretize the real numbers into some size or?
Let's see. The proof does not. No. I've actually stated the entirety of the theorem. This is true. It turns out in the proof, well, somewhere in the guts of the proof, there's a step where you construct something called an epsilon net, which is a very clever discretization. It's sort of in the guts of the proof, but it's not an assumption that you need. So somewhere in the depths of the proof, there's one step that uses a very clever discretization to prove this, but that's not needed as an assumption. Yeah. I should say, back when I was a PhD student, when I was working through this proof, there was sort of a solid week where, I'd wake up and go to the office at 9 a.m., then I'd start reading the book that led up to this proof, and then I'd, read from 9 a.m. to 6 p.m., and then I'd go home, and the next day I'd pick up where I left off, and it sort of took me a whole week that way to understand this proof. So I thought I wouldn't inflict that on you. Okay, so just to tie up a couple of loose ends, what I'm about to do is I'm about to, just mention a few things that will maybe feel a little bit like random facts, but I'm just going to tie up just a couple of loose ends. And so let's see. It turns out that, so I just want to tie this slightly more strongly. So this bound was proved for an algorithm that uses empirical risk minimization, for an algorithm that minimizes 0-1 training error. Trying to decide if I want to do this. You know what? Let's just do this then. So one question that sometimes get asked is, how about support vector machines, right? How come SVMs don't overfit? And in particular, remember our discussion on support vector machines said that you can use kernels and map the features in infinite dimensional feature space. And so it seems like the VC dimension should be, infinite, or n plus 1, n is infinite. So it turns out that the class of linear separators with large margin actually has low VC dimension. I'm going to say this very quickly and informally. It's actually not very important for you to understand the details, but just I'm going to say it very informally. It turns out that I will give you a set of points, and if I ask you to consider only the class of lines that separate these points of a large margin, so my hypothesis class will comprise only linear decision boundaries that separate the points of a large margin, say with a margin at least gamma. Okay, and so I won't allow a point that comes closer, like I won't allow that line because it comes too close to one of my points. It turns out that if I consider if my data points all lie within some sphere of radius r, and if I consider only the class of linear separators that separate the data with a margin of at least gamma, then the VC dimension of this class is less than or equal to r squared over 4 gamma squared plus 1. Okay. So this funny symbol here, that just means rounding up. This is a ceiling symbol. It means rounding up x. And turns out there are some strange things about this result that I'm deliberately not going to talk about. But turns out you can prove that the VC dimension of the class of linear classifiers with large margin is actually bounded. And the surprising thing about this is that this is a bound on VC dimension that has no dependence on the dimension of the points x. So in other words, your data points x can lie in an infinite dimensional space, but so long as you restrict attention to the class of separators with large margin, the VC dimension is bounded. And so in trying to find a large margin separator, in trying to find a line that separates your positive and your negative examples with large margin, it turns out therefore that the support vector machine is automatically trying to find a hypothesis class with small VC dimension, and therefore it does not overfit. Alex?
How is the L2 norm defined on the different dimensional space?
Is actually defined the same way as finite dimensional spaces. So Suppose you have infinite, these are, actually these are countably infinite dimensional vectors, not uncountably infinite dimensional vectors. So, normally the 2 norm squared, right, is equal to sum from y equals 1 to n xi squared. So if x is infinite dimensional, we just define it like that. This is just infinite sum. Say that again?
That could not converge possibly for some vector.
Yes, but although I assume that this is bounded by R.
Oh, okay.
Right, so this ensures that converges. Okay, cool. So just something that people sometimes wonder about. And lastly, to actually tie empirical risk minimization back a little more strongly to the sorts of algorithms we've talked about, it turns out that, let's see. Right. So the theory we've developed so far was really for empirical risk minimization. So that use, and so we focus on just one training example. Let me draw a function that is 0 here, jumps to 1, and looks like that. And so this, for one specific training example, this may be indicator h where the x-axis is z equals theta transpose x. Okay, so for one training example, your training example will be positive or negative, and depending on what the value of theta transpose x is, you either get it right or wrong. And so I guess if your training example, if you have a positive example, then when z is positive, you get it right. Oh, excuse me. I actually want to write not equal to. Okay. Right. Suppose you have a negative example, so y equals 0, right? Then if z, which is theta transpose x, if this is positive, then you will get this example wrong. Whereas if z is negative, then you get this example right. And so this is a plot of indicator h subscript theta x not equals to y. Okay, where right, is equal to g of theta transpose x. Right. Okay. And so it turns out that so what you really like to do is choose parameters theta so as to minimize this step function. You like to choose parameters theta so that you end up with a correct classification on, say, your training example. And so you like indicator h of x not equal y. You like this indicator function to be 0. Turns out, well, this step function is clearly a non-convex function. And so it turns out that just for linear classifiers, minimizing the training error is an NP-hard problem. But it turns out that both logistic regression and support vector machines can be viewed as using a convex approximation to this problem. And in particular, and draw a function like that, it turns out that logistic regression is trying to maximize likelihood, and so it's trying to minimize the minus of the log likelihood. And if you plot the minus of the log likelihood, it actually turns out it'll be a function that looks like this, that is, and this line I just drew, you can think of it as a rough approximation to this step function, which is maybe what you're really trying to minimize if you want to minimize training error. So you can actually think of logistic regression as trying to approximate empirical risk minimization, where instead of using the step function, which is non-convex and gives you a hard optimization problem, it uses this line above, this curve above, to approximate it. So you have a convex optimization problem. You can find the maximum likely estimate parameters for logistic regression. And it turns out support vector machine also can be viewed as approximating this function, but only with a different, let's see. A support vector machine, it turns out, can be viewed as trying to approximate this step function too, but with a different approximation that's linear, and then that's sort of piecewise linear, that yes, horizontally is flat there and then goes up as a linear function there. And that's sometimes called the hinge loss. And so you can think of logistic regression and the support vector machine as different approximations to trying to minimize this, this step function. Okay? And so, and that's why I guess all the theory we developed, even though SVMs and logistic regression aren't exactly doing empirical risk minimization, the theory we develop often gives the completely appropriate intuitions for SVMs and logistic regression. Okay, so that was the last of the loose ends. And if you didn't get this, don't worry too much about it. The high-level message is just that SVMs and logistic regression are reasonable to think of as approximations to empirical risk minimization algorithms. What I want to do next is move on to talk about model selection. Before I do that, let's check for questions about this. Okay, cool. Okay. So, in the theory that we started to develop in the previous lecture and that we sort of wrapped up with the discussion on VC dimension, we saw that there's often a trade-off between bias and variance, right? And in particular, we saw that it's important not to choose a hypothesis that's either too simple or too complex. So if your data has sort of a quadratic structure to it, then if you choose a linear, if you choose a linear function to try to approximate it, then you would underfit. So you have a hypothesis with high bias. And conversely, if you choose a hypothesis that's too complex, then you have high variance, and you will also fail to fit, and you would overfit the data, and you'll also fail to generalize well. So model selection algorithms provide a class of methods to automatically make these trade-offs between bias and variance, right? So remember the cartoon I drew last time of generalization error, I guess, right? I drew this last time, where on the x-axis was model complexity, meaning the number of the degree of the polynomial that you're fitting to a regression function or whatever. And if you have too simple a model, you have high generalization error, that was underfitting. And if you have too complex a model, like fitting a 4th degree polynomial to 5 data points, then you also have high generalization error and you're overfitting. So what I want to do now is actually just talk about model selection in the abstract, all right? And so some examples of model selection problems will include, well, a running example of, let's say you're trying to choose the degree of a polynomial, right? What degree polynomial do you want to choose? Another example of a model selection problem would be if you're trying to choose the parameter tau, which was the bandwidth parameter in locally weighted linear regression, say, right? Or in some sort of locally weighted regression. Yet another model selection problem is if you're trying to choose the parameter c in an SVM, right? And so in the L1 norm soft margin SVM, we had this optimization objective, right? And the parameter c controls the trade-off between how much you want to separate your examples of a large margin versus how much you want to penalize from misclassifying a few examples. So all of these, so these are 3 specific examples of model selection problems, and let's come up with a method for automatically choosing them. So so concretely, let's say you have some finite set of models, and let's write these as M1, M2, M3, and so on, where, for example, this may be, the linear classifier, this may be the quadratic classifier, and so on, okay? Or these may also be discretized. You may also take the bandwidth parameter tau and discretize it into a range of values. And you're trying to choose from amongst a discrete set of values. So let's talk about how you would select an appropriate model. All right. Well, one thing you could do is you can take all of these models and train them on your training set, and then see which model has the lowest training error. Right? So that's a terrible idea. And why is that? Right, cool, because you overfit, right? That was easy. So you laugh when I asked that. Right, so that would be a terrible idea to choose a model by looking at your training set, because, well, obviously you end up choosing the most complex model. Right? You choose a 10th degree polynomial because that's what fits the training set best. So you can't do model selection on a training set. Several standard procedures to do this. One is holdout cross validation. And in holdout cross validation, we take the training set and we randomly split the training set into two subsets. We call the subset, take all the data you have and randomly split it into two subsets. I'm going to call it the training set and the holdout cross validation subset. And then you train each model on just the training subset of it and test it on your holdout cross validation set. And you pick the model with the lowest error on the holdout cross validation subset. Okay, so this is sort of a relatively straightforward procedure that's commonly used where you train on 70% of the data, then test all your models on 30% and pick whatever has the smallest holdout cross validation error. And after this, you actually have a choice. You can actually, having taken all of these hypotheses trained on 70% of the data, you can actually just output the hypothesis that has the lowest error on your holdout cross validation set. And optionally, you can actually take the model that you selected and go back and retrain it on all 100% of the data. Okay, so both versions are actually done reasonably often. You can either just take the best hypothesis that was trained on 70% of the data and just output that as you find the hypothesis, or you can use this to say, having chosen the degree of the polynomial you want to fit, you can then go back and retrain the model on the entire 100% of the data. And both of these are commonly done. So holdout cross validation works great, and sometimes you're working with a company or with an application or something. There are many machine learning applications where you have very little data, or where every training example you have was painfully acquired at great cost, right? Sometimes your data is acquired by medical experiments, and each training example represents a significant amount of physical human pain or something, right? And so when you talk to them and say, well, I'm going to hold out 30% of your data set just to select my model, the people you're working with, sometimes that causes unhappiness. And so maybe you want to not have to leave out 30% of your data just to do model selection. So there are a couple of other variations on holdout cross validation that make sometimes slightly more efficient use of the data. And one is called k-fold cross validation. And here's the idea. I'm going to take all my data S, right? So Imagine I'm going to draw this box S, because to denote the entirety of all the data I have. And I'll then divide it into k pieces. And this is 5 pieces in what I've drawn. And what I'll do is I will repeatedly train on k minus 1 pieces, test on the remaining one. Test on the remaining piece, I guess. Right, and then you average, over the k results, I guess. Okay. So in other words, I will first hold out, say the first, excuse me, I would hold out, say, the first 1/5 of my data, and then I train on the remaining 4/5, and I'll test on the first 1/5. And then I'll then go and hold out the second 1/5 of my data, and I'll train the remaining 4 pieces and test on this. Then I'll remove the third piece, train on the other 4, test on this, and so on. I'll do this 5 times, and this will, and then I'll take the 5 error measures I have, and I'll average them, and this then gives me an estimate of the generalization error of my model. Okay, and then again, when you do k-fold cross-validation, usually you then go back and retrain the model you selected on the entirety of your training set. So I drew 5 pieces here because that was easier for me to draw, but k equals 10 is very common. Okay, so I should say k equals 10 is a fairly common choice to do 10-fold cross-validation. And the advantage of this over whole-out cross-validation is that if you split your data into 10 pieces, then each time you're only holding out 1/10 of your data rather than, say 30% of your data. I say in simple whole-out cross-validation, a 30-70 split is fairly common. Sometimes like a 2/3, 1/3, or a 70-30 split is fairly common. And if you use k-fold cross-validation, k equals 5, or more commonly k equals 10 is the most common choice. The disadvantage of k-fold cross-validation is that it can be much more computationally expensive. In particular, to evaluate your model, you now need to train your model 10 times instead of just once. And so you need to run logistic regression 10 times per model rather than just once. And so this is computationally more expensive. But k equals 10 works great. And then finally, there's actually a version of this that you can take even further, which is when you set k equals m. And so that's when you take your training set and you split it into as many pieces as you have training examples. And this procedure is called leave one out cross-validation. And what you do is you then take out the first training example, train on the rest, and test on the first example. Then you take out the second training example, train on the rest, and test on the second example. Then you take out the third example, train on everything but your third example, test on the third example, and so on. And so with this many pieces, you're now making maybe even more effective use of your data than k-fold cross-validation. But clearly, leave one out cross-validation is computationally very expensive because now you need to repeatedly leave one example out and then run your learning algorithm on m-1 training examples. You need to do this a lot of times. And so this is computationally very expensive. And typically, this is done only when you're extremely data scarce. So if you have a learning problem where you have, say, 15 training examples or something, then if you have very few training examples, leave one out cross-validation is maybe preferred. Yeah.
In the last part, you proved that the difference between the generalizer and bounded by number of samples in the training set and BC dimension. So maybe we can, instead of splitting our samples into different groups, we can use that formula. We apply compute the training error and use that formula for computing the upper bound for generalizer.
Yeah, that's done, but yeah, in practice, I personally tend not to do that. It tends not to be the VC dimension bounds are somewhat loose bounds, and so there are people, structural risk minimization, that propose what you do, but I personally tend not to do that. Okay, So let me actually, are there questions about cross validation? Oh, yeah.
Just to kind of follow up on that, because I mean, we spend all this time sort of deriving that expression for the, for how many data points you sort of need to go into a certain marginal lab.
Right.
So it seems like one ought to be able to use that to sort of do this sort of more analytically, I guess. I mean,
yeah.
Isn't that kind of the point in some ways?
No, okay, so let me answer that one. So it turns out that when you're proving learning theory bounds, very often the bounds will be extremely loose because you're sort of proving a worst case upper bound that holds true even for very bad, what was it? So the bound I proved just now, right, that holds true for absolutely any probability distribution over training examples, right? So I just assumed that training examples were drawn IID from some distribution script D, and the bounds I proved hold true for absolutely any probability distribution over script D. And chances are whatever real life distribution you get over houses and their prices or whatever is probably not as bad as the very worst one you could have gotten, right? And so it turns out that if you actually plug in the constants in learning theory bounds, you often get extremely large numbers. So if you actually say take logistic regression, logistic regression have 10 parameters and I want 0.01 error and with 95% probability. How many training examples do I need? If you actually plug in actual constants into the textbook learning theory bounds, you often get extremely pessimistic estimates of the number of examples you need. You end up with sort of ridiculously large numbers. You need 10,000 training examples to fit 10 parameters or something. A good way to think of these learning theory bounds is, and this is why also when I write papers in learning theory bounds, I quite often use big O notation to just ignore the constant factors because the bounds tend to be very loose. There are some attempts to use these bounds to give guidelines as to what model to choose and so on, but I personally tend to use the bounds. I personally tend to use the bounds to gain intuition about, for example, whether the number of training examples you need grows linearly in the number of parameters, or whether it grows exponentially in the number of parameters, whether it goes quadratically in the number of parameters. So it's quite often the shape of the bounds, the fact that the number of training examples, the fact that sample complexity is linear in a VC dimension. That's sort of a useful intuition you can get from these theories, but the actual magnitude of the bound will tend to be much looser than will hold true for a particular problem that you're working on. Does that answer your question? Yeah. Right. Yeah. And it turns out, by the way, so for myself, right, rule of thumb that I often use is if you're trying to fit a logistic regression model, if you have n parameters or n plus 1 parameters, if the number of training examples is, say, 10 times your number of parameters, then you're probably in good shape. And if your number of training examples is like 20 times the number of parameters, then you're probably perfectly fine fitting that model. Right? So those are the sorts of intuitions that you can get from these bounds. So,
in cross-validation, do we split these samples randomly?
Yes. Yes. So by convention, we usually split train test splits randomly. Okay, cool. So, one more thing I want to talk about for model selection is actually a special case of model selection. It's called the feature selection problem. And so here's the intuition. For many machine learning problems, you may have a very high dimensional feature space with very high dimensional x's, vector input feature x's. So for example, for text classification, when we talk about the text classification examples, the spam versus non-spam, you may easily have on the order of 30,000 or 50,000 features. I think I used 50,000 in my early examples. So if you have so many features, you have 50,000 features, depending on what learning algorithm you use, right? There may be a real risk of overfitting. And so if you can reduce the number of features, maybe you can reduce the variance of your learning algorithm and reduce the risk of overfitting. And for the specific case of text classification, if you imagine that maybe there's a small number of, quote, relevant features, right? So there are all these English words, and many of these English words probably don't tell you anything at all about whether the email is spam or non-spam. Like the word, for English function words like the, of, a, and, these are probably words that don't tell you anything about whether the email is spam or non-spam. So, whereas in contrast, there'll be a much smaller number of features that are truly, quote, relevant to the learning problem. So for example, you see the word bi or Viagra, those are words that are very useful for telling you whether something is spam or non-spam. You see the word Stanford or machine learning or your own personal name. These are other words that are useful for telling you whether something is spam or non-spam. Right? So in feature selection, we would like to select a subset of the features that are maybe, hopefully, the most relevant ones for a specific learning problem, so as to give ourselves a simpler hypothesis class to choose from, and therefore reduce the risk of overfitting, even when we have 50,000, even when we may have had 50,000 features originally, say. So how do we do this? Well, if you have n features, right, then there are 2 to the n possible subsets. Right, because each of your n features can either be included or excluded. So there are 2 to the n possibilities, and this is a huge space. So in feature selection, what we most commonly do is use various search heuristics, so simple search algorithms, to try to search through this space of 2 to the n possible subsets of features, to try to find a good subset of features, because this is too large a number to enumerate all possible feature subsets. And as a concrete example, this is the forward search algorithm. It's also called the forward selection algorithm. It's actually pretty simple, but I'll just write it out. My writing out will make it look more complicated than it really is, but starts with initialize your set stripped f to be the empty set, and then repeat, for I equals 1 to n, try adding feature I to the set stripped f, and evaluate the model using cross-validation. And by cross-validation, I mean any of the 3 flavors, be it simple holdout cross-validation, or k-fold cross-validation, or leaf one-out cross-validation. And then, set f to be equal to f union, I guess, and then the best feature, found in step 1, I guess. Okay. And finally, you would so for selection, this procedure is start off with the empty set of features, and then on each iteration, this is the word try, take each of your features that isn't already in your set stripped f, and you try adding that feature to your set. Then you train the model and evaluate the model using cross-validation, and basically figure out what is the best single feature to add to your set stripped f. Then in step 2 here, you go ahead and add that feature to your set stripped f, and you iterate. And when I say best feature or best model here, by best I really mean the best model according to holdout cross-validation. By best I really mean the single feature addition that results in the lowest holdout cross-validation error, the lowest cross-validation error. So you do this, adding one feature at a time, and when you terminate this loop is if you've added all the features to F. So if F is now the entire set of features, then you can terminate this. Or if via some rule of thumb, you know that you probably don't ever want more than K features, you can also terminate this if F has already exceeded some threshold number of features, right? So maybe if you have 100 training examples and you're fitting logistic regression, you probably know you won't want more than 100 features, and so stop after you have 100 features added to the set F, say. Okay. And then finally, having done this, I said output the best hypothesis found. And again, by best, I mean when running this algorithm, you'll be seeing lots of hypotheses. You'll be training lots of hypotheses and testing them using cross-validation. So when I say output best hypothesis found, I mean of all the hypotheses you've seen during this entire procedure, pick the one with the lowest cross-validation error that you saw. Okay? So that's forward selection. Let's see, just to give this a name, this is an instance of what's called wrapper feature selection. And the term wrapper comes to the fact that this feature selection algorithm that I just described, the forward selection or forward search, is a piece of software that you write that wraps around your learning algorithm, right? In the sense that to perform forward selection, you need to repeatedly make calls to your learning algorithm to train your model using different subsets of features. Okay, so this is called wrapper model feature selection, and it tends to be somewhat computationally expensive because as you're performing the search process, you're repeatedly training your learning algorithm over and over and over on all of these different subsets of features. Just mention also there is a variation of this called backward search or backward selection, which is where you start with F equals the entire set of features and you delete features one at a time. Right. And so that's backward search or backward selection. And this is another feature selection algorithm that you might use. Part of whether this makes sense is really, there'll be problems where it really doesn't even make sense to initialize F to be the set of all features. So if you have 100 training examples and 10,000 features, which may well happen, right? 100 emails and 10,000 features in email, but 100 training examples, then depending on the learning algorithm you're using, it may or may not make sense to initialize the set F to be all features and train the model using all features. And if it doesn't make sense to even train the model using all features, then forward selection would be more common. So let's see. Wrapper model feature selection algorithms tend to work well. And in particular, they actually often work better than a different class of algorithms we're going to talk about now. But their main disadvantage is that they're computationally very expensive. Other questions about this before I talk about the other? Yeah.
Forward search, it might not find the best combination.
Yeah. Yes, you're absolutely right. So forward search and backward search, both of these are search heuristics, and you cannot, for either of these, you cannot guarantee they'll find the best subset of features. It actually turns out that, under many formalizations of the feature selection problem, it actually turns out to be an NP-hard problem to find the best subset of features. But in practice, forward search and backward search work fine. And you can also envision other search algorithms where you sort of have other methods to search through the space of 2 to the n possible feature subsets. Okay. So let's see. Because forward selection is, so forward selection, excuse me, rapid feature selection tends to work well when you can afford to do it computationally. But for problems such as text classification, it turns out for text classification specifically, because you have so many features and easily have 50,000 features, forward selection would probably be very expensive. So there's a different class of algorithms that will give you, that tends not to do as well in the sense of generalization error. So you tend to learn a hypothesis that works less well, but is computationally much less expensive. And these are called the filter feature selection methods. And the basic idea is that for each feature I, we'll compute some measure of how informative, right, xi is about y. Okay. And to do this, we'll use some simple heuristics, say that for every feature, we'll just try to compute some rough estimate, or compute, wow, handwriting is really bad, sorry. Compute some measure of how informative compute some measure of how informative xi is about y. So there are many ways you can do this. One way that you can choose is to just compute the correlation between xi and y. You just, for each of your features, just see how correlated this is with your class label y. And then you just pick the top k most correlated features. Another way to do this see. Right. So for the case of let's see, for the case of text classification, there's one other method, or actually especially for discrete features, I guess, there's one other informativeness measure that's used very commonly, which is called mutual information. You get to play with some of these ideas more in problem sets, but I'll just say this very briefly. So the mutual information between the feature xi and y, well, I'll just write out the definition, I guess. Let's say this is text classification, so x can take on two values, 0, 1. The mutual information between xi and y is defined as sum over all possible values of x, sum over all possible values of y, times the distribution times that, where you would, excuse me, this should be xi, I guess. Okay, where all of these distributions, where sort of the joint distribution over xi and y, you would estimate from your training data. Right, all of these things, these as well. You'd estimate from your training data what is the probability that x is 0, what's the probability that x is 1, what's the probability that x is 0, y is 0, x is 1, y is 0, and so on. So it turns out that, let's see, it turns out there's a standard information theoretic measure of how different probability distributions are. And I'm not going to prove this here, but it turns out that this mutual information is is actually so the standard, measure of how different two distributions are called the KL divergence. If you take a class in information theory, you have seen concepts like mutual information and KL divergence, but if you haven't, don't worry about it. Just the intuition is there's something called KL divergence. There's a formal measure of how different two probability distributions are. And mutual information is a measure for how different the distribution P of x, the joint distribution is of x and y, from the distribution you would get if you were to assume they were independent. Okay, so if x and y were independent, then P of x comma y would be equal to P of x times P of y. And so, this distribution and this distribution would be identical, and the KL divergence would be 0. In contrast, if x and y were very non-independent, in other words, if x and y are very informative about each other, then this KL divergence will be large. And so mutual information is a formal measure of how non-independent x and y are. And if x and y are highly non-independent, then that means that x will presumably tell you something about y, and so they'll have large mutual information. And this measure of informativeness will tell you x might be a good feature. You get to play with some of these ideas more in the problem set, so I won't say much more about it. And what you do then is, having chosen some measure like correlation or mutual information or something else, you then pick the top k features, meaning that you compute correlation between xi and y for all the features, or mutual information between xi and y for all the features, and then you include in your learning algorithm the k features of the largest correlation of the label, or of the largest mutual information of the label, whatever. And to choose k, you can actually use cross-validation as well. Okay? So you would take all your features and sort them in decreasing order of mutual information, say, and then you try using just the top 1 feature, the top 2 features, the top 3 features, and so on, and you decide how many features to include using cross-validation. Okay? Or sometimes you can just choose this by hand as well, either way. Okay, other questions about this? Okay, cool, great. So next lecture, I'll wrap up the Bayesian model selection, but let's close with the then. Thanks.